infinite horizon real-time planning for repetitive tasks, and Fahad Islam will present.
Hello. Okay, I'm Fahad Islam, and today I'm presenting provable indefinite horizon real-time planning for repetitive tasks. This is joint work with Oren Salzman and Max Likashev, my advisor from Carnegie Mellon University. So we are motivated by motion planning problems in warehouse settings where the tasks typically are very repetitive, yet performance critical, so we need fast planning times. I'll show you a few examples of such domains. So here, this robot is working on a conveyor belt where the objects are coming in at a fairly high speed, and the task here is to pick up these objects and then put them in different bins. Now, the robot has a fixed time budget to plan within. If it fails to plan within that time budget, then did the video play or no? Okay. So if it fails to plan within that time, then it will miss objects, and we don't want that to happen. So we want robust and efficient motion planning. So here is a second example. It's an industrial robot working in a warehouse setting where the robot has to perform a sorting tasks. So it is picking up objects and then sorting them in these cubby shelves that you saw. So again, to have a good efficiency in such warehouse, it's critical, and we want fast planning times. Finally, in this last example, this is a project that we are doing in collaboration with Honeywell and NREC at CMU. It's a truck unloading robot that you see. The task here is to unload boxes from these delivery containers, and we want to increase the throughput of the system. So we want to increase the rate at which the robot is unloading boxes. So again, we don't want extra delays or overheads because of lazy motion planning. So in all these domains, we observe that motion planning needs to be fast and often provably bounded in time. We also observe that the environment is fairly structured, and the models, like the environment is known. So we won't see any objects online that we don't have a model of. And finally, we observe that the tasks are very repetitive. So the question that we are asking ourselves is, can we provide provably bounded planning times by leveraging pre-processing, given the environments that we are dealing with are known? And to the best of our knowledge, none of the existing algorithms provide such guarantees on planning time. So to formulate our problem, we make the following assumptions about the domain. We assume that the environment is known, as I explained, so the robot will not see any object online that it doesn't have a model of. We assume that we have a set of start configurations. So for example, again, in this conveyor example, the start configuration can correspond to the drop-off positions where the robot is dropping off objects. Again, in this truck unloading domain, the drop-off position, the start configuration is the configuration of the robot where it unloads the boxes. And corresponding to each start configuration, we have goal regions. The reason we need goal regions is we want to allow perturbations in the goal poses. For example, again, in this conveyor domain, the object that is coming in can be a different X, Y position and orientation, and we want to be able to handle that. So now we have an idea of what kind of setting we are dealing with. Here is a 2D example of the same setting. We have a start state. We have a goal region, which is shown as this dashed region, and we have some obstacles which are shown in red. So the first thing that we do is we discretize the goal region so that we have finite number of states in the goal region. Now, one could think of that, why can't we just enumerate all the states in the goal region and pre-compute paths from the start state to each of those? The problem is that in this 2D example, it's possible. For higher dimensions, we will very quickly run out of memory. Also, if you have like 1 million states in the goal region, it'll take forever to pre-compute these plans. So can we do something better? So the key insight of this work is that given a potential or a heuristic function in some attractor state, typically there is a large region around that state within which the states can reach the attractor state following that potential or heuristic function. We call these states as reachable states, which are marked as these white states in the region. So instead of having to pre-compute paths to all the states within this region, we only need to pre-compute a path to the attractor state, and then at the query time, we'll use the potential function to find a path from any goal state that may lie in this region to the attractor state. And then we'll combine the two paths, pi I, and the path given by the potential function to get the final path from start to the goal. Now, another point is that you can think of this method as a compression mechanism. So instead of having to pre-compute paths to all the states in the goal region, we want to compute a minimal set of paths which can still cover the goal region. And the quality of this compression depends on the quality of the heuristic function that we're using here. The better, the more informed the heuristic function is, the larger the regions we'll get, and the lesser the number of paths we'll have to pre-compute. Now, once we construct one such region, we have to construct multiple similar regions, ensuring that no state in the goal region is left free. So every state is covered by at least one subregion. So more formally, we decompose G into a set of subregions R1 to K, each defined by an attractor state in a radius, such that the union of all these regions R1 to K completely covers G. Now, this was the pre-processing phase. Now, what will happen in the query phase? Now, once we have these regions that we have pre-processed, we get a query, which is a goal state. The first thing we do is we identify which subregion this goal state belongs to using the radii of these regions. And then we simply follow the potential function, which will lead us to the attractor state. And the way we construct these subregions ensures that we don't have to do any collision checking in this step, which is typically the most expensive step in motion planning. And then we just combine this path pi G with the pre-computed path pi I to get the final path from the start to the goal. So this was the overview. Now let's look into some of the related work in this domain. So our algorithm at a high level falls in the class of pre-processing based motion planners. The most renowned among them in the motion planning community are probabilistic roadmaps from 90s. So PRMs construct a roadmap in the continuous space by randomly sampling states in the free space and trying to connect them. And at the query time, they try to connect the start and the goal state to this roadmap and use any graph search algorithm to find a path from the start to the goal. But these class of planners they provide asymptotic guarantees, and we are looking into more deterministic guarantees. Subgoal graphs also construct a roadmap, but in a grid world, in a discretized space. Similar to our method, it identifies a set of attractor states and then construct a roadmap or a subgoal graph from those attractor states, maintaining the property that every two states which are connected by an edge on this sparse subgoal graph are reachable. So they can use this subgoal graph online to improve the planning efficiency. But for two reasons, this algorithm is not applicable to our setting. One is that they require pre-processing the entire state space, which is not possible for memory limitations for higher dimensions. So it's only applicable to 2D or at maximum 3D domains. Second is that at the query time, they require running a Dijkstra-like search to connect the start and the goal state to this subgoal graph, due to which we cannot provide bounds on the planning time. Similar ideas were also explored in the controls community. These listed papers, they distribute the configuration space into control-specific regions, and online they use region-specific policies for robust and safe execution in these local regions of the configuration space. And these were the papers that inspired us for this work. Finally, in the context of bounded time planning, there is a family of planners called real-time planners. They provide bounds on the planning time, but they only plan for a finite horizon, giving partial paths, and then they typically interleave planning and execution. So we see that none of these algorithms provide bounds on the planning time for problems which are of indefinite horizon. Now let's look into some of the details of the pre-processing step. Again, we have a start, we have a goal region and some obstacles. The first thing we do is we arbitrarily pick an attractor state from the goal region. And then we pre-compute a path from the start state to the attractor state. And this can be done using any off-the-shelf motion planner. It doesn't have to necessarily be a search-based planner. Then we have to construct the subregion for this attractor state. Now, recall that we define reachable states as the states which can reach the attractor state following the potential function. So it turns out we can compute this region very efficiently using a single Dijkstra-like search by using a recursive rule that I'll explain in a bit. So what we do is we run a search from the attractor state and expand states in the order of not the g values, but the heuristic values. And the heuristic here is the Euclidean distance to the attractor state. I'll show you a little animation of this search. Now let's analyze what happens in a single iteration of this search. So assume that we have already marked these white states as reachable. Now for a newly expanded state, we see if the best predecessor of this state, according to the heuristic function and some tie-breaking criterion, is reachable or not. If that predecessor state is reachable, then we label this state also as reachable. And we use this recursive rule in this search to label all the states which are reachable for this attractor state. Now the search continues, and it then terminates when we find the first state which is unreachable. So the unreachable state obviously is the state which cannot reach the attractor function following the heuristic. More specifically, for this state, the best predecessor according to the heuristic function leads to a collision. So we stop here, and the heuristic value of this state gives us the radius of this subregion. Now, because we expand states in the order of the minimum heuristic values, we guarantee that all the states which have heuristic value less than the heuristic value of the last expanded states are contained in this region, and they are reachable, which are shown as these white states. Now, after the first region is constructed, we sample another attractor state in the region in anywhere in G in the area which is yet to be covered, and the process goes on and on until we get full coverage of the goal region. Now let's look into some of the theoretical properties that we provide. Our approach is resolution complete in G, meaning that with respect to certain resolution that we come up with, for any goal state that lies in G, if a path exists from the start state, the algorithm will guarantee that it provides that path. We show a query time complexity of order of the number of regions that we pre-process plus the product of the depth of the largest subregion and the branching factor. So the depth of the subregion here is, it corresponds to the number of states that you will have to expand at query time if the goal state happens to lie on the boundary of the largest subregion. So it's the worst case. So you can analyze this complexity easily. So at query time, given the query state, we have, in the worst case, we'll have to do a search over all the regions to identify which subregion the state belongs to. And then in the worst case, we'll have to perform D expansions with B as a branching factor. And that's our complexity. That's all. We also provide a suboptimality bound, assuming that the planner that we use for pre-computing these paths, Pi, is optimal. We provide this additive suboptimality bound. So the difference between the cost of the optimal plan and the plan that our planner generates is no more than 2 times the cost of this path pi g that the potential function gives us at the query time. We evaluated our approach on 7 degrees of freedom motion planning problem for this PR2 robot. So the task here is that the robot has to pick up mail from the carts. It's a mail sorting task, and then place them in these cubby shelves. So we define the goal region in this problem in the task space of the robot. So the goal can be any arbitrary position and orientation within these cubby shelves. For the experiments, we randomly sample states. We randomly sample poses in these cubby shelves to get our results. We compared our approach against probabilistic roadmaps, and MQRRT. MQRRT is a multi-query variant of RRT which we came up with. So in the pre-processing step, we generate a very dense RRT tree rooted at the start state, and at the query time, given the goal state, we try to connect the goal state to k nearest states in the RRT tree. And if it fails to find a connection, then it's a failure. For PRM, again, we also construct a dense roadmap offline, and we add the goal state, the PRM in the pre-processing step, the start state, and at the query time, we just try connecting the goal state to the PRM, and if the connection fails, or if the start and the goal belong to different connected components of the PRM, then it's a failure. We also compared with experience graphs, which is a search-based planning algorithm that uses experience to improve planning efficiency, and RRT Connect. We observed that our algorithm takes about 24 minutes to pre-process the goal region in this domain. And we allow PRM and MQRT, which are the two other pre-processing based algorithms, to use 4x the time that we give our method, so about 2 hours. And we observed that none of the other 4 methods reach a success rate of more than 90%. Also, we show an improvement of planning times of over an order of magnitude over PRM and MQRT, which are the fastest amongst the other planners. In terms of memory usage, for this domain, our method only consumes 7.8 megabytes to pre-process this region. On the other hand, you can see that the PRM consumes about 2 GBs of memory. Now, to the bottom left, this is the plot that shows the pre-processing time versus the memory usage. And as you would expect, as the pre-processing time grows, the memory requirement of PRM and MQRT increases, whereas the memory requirement of our method is shown as this cross here. To the bottom right is the plot that shows pre-processing time versus the success rate. And as the pre-processing time increases, the success rate of these algorithms increase. But if you notice, for instance, for PRM, it starts to plateau over here. The reason is that typically sampling-based planners suffer from narrow passages in the configuration space. And of course, we have a success rate of 100%. In conclusion, we proposed a pre-processing based method to provide provably bounded planning times for a given environment. And we evaluated our approach on 7-DOF motion planning problem. In the future work, we want to extend this approach for environments which are not completely static, but we want to allow some perturbations. We can explore how we can intelligently sample these attractor states to get better compression. We can also look into how we can utilize multiple heuristics instead of having a single heuristic function. And if possibly, we can provide bounds on the memory requirements. So with that, I'll conclude, and I'll be happy to take any questions.
Thank you for the nice talk. I didn't get the connection between the very exciting motivating examples and the actual method, because the motivating examples also seemed time variant, but your formalization here is just configuration space and not configuration cross time. And the other question I have is, you're trying dense roadmaps. Why not try sparse roadmaps? There's a lot of tools in that area as well, so as not to have the issues with the density.
Right. So referring to the first question, if you're referring to the conveyor domain, where the objects are coming, so it's a dynamic environment. So if currently we are looking into exactly the same problem, how we can solve that using our approach. So if you think about it, if we include time as a dimension for planning, the environment becomes static. So if you know the object that is coming in.
But can you still pre-process the goal and know the goal perfectly? Even in the example that you showed in your results, once you put the mail inside there, you have new obstacles as well inside the goal region. So how can you trust the pre-processing that you have done without the new obstacles?
In the mailroom scenario? So the video that I showed you in the beginning, you have scenarios where the objects that you put, they just flow through they are on inclined surfaces, so they just go away when you put them. Also, the example that we give is in a mailroom environment. So typically, the mails don't collide with one another. It's picking up an envelope, and then it's placing them in these cubby shelves. So if you place the first envelope, the second one will not collide with the first one, right?
So you have to have this property
Right.
in terms of,
Yeah,
and yeah, the density on the roadmaps goes.
right.
Do you know the sparse methods?
Yeah, so you're talking about sparse 2 and sparse from OMPL. Yeah, I mean, we didn't experiment with that, but definitely you can reduce the memory requirement by using those instead of using PRMs. So one way we could compress also the requirement of memory from PRM is that we can, like we did that here. So we pre-computed paths from every state in the roadmap to the start state. So we don't have to construct the whole, we don't have to store the whole roadmap. We only need paths, right? Because the start state is fixed. So that we did here. But yeah, definitely you can reduce the memory requirements, but still it's you cannot provide completeness guarantees. Right, yeah.
Okay, if there are not other questions, we can thank again the speaker and switch to the next one.